So there are lots of real-world applications where I see a whole bunch of runs of some data generating process, and I want to decide, okay, for example, maybe these are flips of a coin, and I want to know, is this coin fair or not, based on the flips I see? Or maybe I have two sequences, and I want to know, maybe these are like lifetimes of a battery before and after I change my manufacturing process, and I want to know, is this battery, a longer life than this battery, right, statistically? Or does this signal have a different distribution than that signal? So all these things are instances of generally what's called hypothesis testing. And you could take a whole course on hypothesis testing. That course might, for example, be called something like detection and estimation, usually like at a graduate level. It's all super important in machine learning, pattern recognition, computer vision. And so what I want to do in these next few lessons is use some of the tools of basic probability that we've accumulated so far to answer some simple hypothesis testing kinds of questions. And the first one is called significance testing. So it's kind of like a special case. And the setup here is that I have what I call the null hypothesis, which I'm going to call H0. And what I have to do is I have to decide, am I going to accept that this hypothesis is true, or I'm going to reject it? Okay. So for example, maybe my null hypothesis is that I have a fair coin. And what I'm going to do is I'm going to look at some sort of a, what I call a statistic involving all of my experiments. So suppose I look at the sum of a bunch of flips of this coin. And then I'd say, okay, well, suppose I did 100 coin flips. I know that my mean should be about 50, right? And so if my number is 23 or 78, I probably know that my coin is not fair. But if it's 52 or 48, maybe I think it's okay. So the idea is, how can we make a principled argument for whether we should accept or reject the null hypothesis? Okay. So to be a little more precise, the idea is that I'm going to look at this number and I'm going to design a region, and I'm going to say, okay, if Sn is in the region, then I'm going to reject the hypothesis. And if Sn is not in the region, I'm going to accept the hypothesis, right? And this is kind of like a decision rule. It says, okay, if I'm in this category, reject. If I'm in this category, accept. Okay. And so in order to design these kinds of decision rules, we need to think about the ways that our decision can be wrong, right? We talked about this a little bit early on. So we have what's called type 1 error. This means that we rejected the null hypothesis when it was true. And we have a type 2 error, which is that we rejected or we accepted the hypothesis when it was false, right? Those are the two ways that we can be wrong. Okay. And so basically what we have are kind of like misses and false alarms. Okay. So I'm assuming that I know H0. That is, I know how the coin should behave when it's a fair coin. But there are lots of ways the coin could behave when it's unfair, right? All I really know is what should it do in the case that H0 is true, right? So really, the only thing that I can then work with is what's called the type 1 error, right? I can't really say much about the type 2 error because I don't know all the ways that H0 can be wrong, right? So significance testing is about basically I put a bound on the type 1 error and I find out what my region should be. So let me be precise. It's like saying alpha is going to be basically our type 1 error, which is, well, I guess it's alpha is the probability of a type 1 error, right? And I can evaluate that by saying, okay, if I have some region where I reject the null hypothesis, right? This is like the rejection region. Then I integrate my PDF under the null hypothesis, like a class conditional kind of probability. And this is the probability of making a mistake, right? That's saying that H0 was true, but I rejected it. And so then what I can do is I can say, okay, a more a smaller alpha would lead to a more conservative range of accepting the hypothesis, right? That's like saying I'm super scared of rejecting the hypothesis, so I basically just like always say it's true, right? Because I want to avoid making any mistakes. Whereas maybe if I'm more willing to make mistakes, then my decision region changes, okay? So this alpha is basically the same alpha as we had when we were talking about confidence intervals a few lessons ago. And in a similar way, we can use Q functions and so on to try to actually get numbers. So let me be concrete about this example, right? So let's suppose that the null hypothesis is that the coin is fair, right? That is, I have a Bernoulli random variable with p equals 1/2, right? Now I'm going to look at S100, which is the sum of 100 flips, with 1 being ahead and 0 being not ahead, right? So what I want to do is find a significance test. Significance test at a level of, say, 5%. Okay. What this means is that I want to find alpha equals 0.05, which is the probability of rejecting H0 when H0 is true. And really, this probability is related to a region where I'm basically going to say, plus or minus some constant c outside of the expected value, which is 50, is when I'm going to, if I'm in this region, I accept that the hypothesis is true. Outside, I reject it, right? So I can kind of like now work on these probabilities. And since 100 is a lot of coin flips, I know that the central limit theorem should give me a pretty good, accurate probability in the tails of the distribution, right? That's like saying I want to have 0.05 be the probability that the sum is not equal to, not in this range, when H0 is true, right? That's like saying I get some crazy set of coin flips that gives me 78 heads even though the coin was fair, right? What's the probability of that happening? I'm just going to kind of rewrite this, and this should be familiar from the central limit theorem kind of lectures, right? Or a different way of saying this is that if I divide everything through by 100, that the mean minus 1/2 is greater than this. And so now I can kind of use my Q tables to say, okay, I know what this is. This is like saying, okay, I want to have the sum of these two tails be 0.05, right? So it's like saying I want 2Q of Z to equal 0.05. Then I can look in my Q table and I can find out that the corresponding Z value here is 1.96. We had this actually from some of our previous tables. I don't have it on the screen right now, but we remember we had this table that said, what is the inverse of 0.25? It turned out to be this, right? And then I can use this to say, okay, this number here corresponds to Z sigma square root of n. What don't I know? I don't know C, right? So really what I do is I want to say C is equal to 100 times the Z times the sigma. I know that sigma for a Bernoulli random variable should be 1/2, and I divide by the square root of n, which is 100 flips, right? So I'm going to have basically 10 times what's roughly 2 divided by 2. So basically I can say that C here is going to be 10. And that tells me that my significance test at a level of 0.05 is in the range 40 to 60. Okay, and so this is all well and good. And in the next lesson I'm going to say, well, what happens when I can also characterize the alternate hypothesis? This is like saying, maybe I know either the coin is fair or it's a coin that has probability p equals 3/4. How could I distinguish which coin I have from seeing a whole bunch of coin flips? So tune in next time.